Welcome to the next installment of Advanced Chemistry Lectures. Today I will do the third lecture in the scaled back, more basic version on coordination chemistry. Specifically, I will talk about part 2 of this lecture on phosphine ligands, Bent's rule, and their application to transition metal complexes. And so one observation or one concept I talked about in part 1 of this lecture was the idea that bigger phosphines are some of the best donors. And this seems a little bit counterintuitive to people. If the phosphine's really big, how is it going to be able to actually access the transition metal center and dump so much electron density onto the metal? And the reason it can do this is if the phosphine features very large R groups, what happens is that the R groups have to move away from one another. If the R groups move away from one another, the C, P, C angles get larger. If the C, P, C angles get larger, there's more S character in the individual P, C bonds. And what that does is it leaves more P character in the lone pair. If we now look at something like trimethylphosphine, you now have very small methyl groups. The methyl groups don't have to really move away from one another. And in the extreme case, and if they were the C, P, C angles were 90 degrees, that would be pure P character in the individual bonds. That would leave the lone pair with a large degree of S character. And so in really big phosphines, the phosphorus center starts to flatten out and almost look like it's sp2. Well, if the phosphorus center is sp2, that means the lone pair is then entirely in a pure p orbital. If a lone pair is in a p orbital, it is highly basic, highly nucleophilic, and is going to dump its electron density on a transition metal center. And you can see this out experimentally by looking at the CO stretching frequency. And so if you focus on the CO stretching frequency, what you'll notice is that the best donors feature the smallest CO stretches and sort of the smallest CO stretching frequencies. And so why is that? Well, the reason for this is really nicely shown in this kind of pseudo-resonance structure shown here. Well, if you have a phosphine that's a really good donor, it's dumping electron density on the transition metal center. Well, that transition metal center can engage in back bonding to the carbon monoxide moiety. Well, the more electron density that is on the metal, the more back bonding that occurs. The more back bonding that occurs, the more the MC single bond starts to look like an MC double bond. Well, at the same time that it's dumping electron density onto CO, notice that it's dumping into an anti-bonding orbital on CO. Well, the more electron density you dump into an anti-bonding orbital, the more that CO triple bond now starts to look like a CO double bond. The more it starts to look like a CO double bond, the more the CO stretching frequency will drop. And you can see that in tritert-butylphosphine, it drops to 2056. In trimethylphosphine, it doesn't drop as far, it drops to 2064. And this is because tritert-butylphosphine is dumping so much electron density on the metal center that is facilitating a large degree of back bonding. The more back bonding you get, the more the MC bond starts to look like a double bond. Well, if the MC double bond starts to look more like a double bond, the CO bond must look like more like a double bond, and that's going to result in a drop in the CO stretching frequency. And so what we kind of know intuitively is how big some of the most basic phosphines are. If we talk trimethylphosphine versus triethylphosphine versus triisopropyl versus tricyclohexyl versus tritert-butyl, I think everybody fundamentally understands that methyl is the smallest, followed by ethyl. Isopropyl and cyclohexyl are sort of similar in size. Cyclohexyl is bigger, and then tert-butyl is the biggest. But what if you have more exotic phosphines? You have ones, let's say chiral phosphines, that feature 3 different R groups. Or you don't really fully understand how big the actual R group is. Can you actually evaluate the size of the phosphine? And you can. And you can evaluate this. And originally, this was actually done like on a piece of paper, building models, and you could actually see that the larger the phosphine was, the bigger the cone was. And the cone we're talking about is the cone shown here. And so if the MP bond length was normalized to be about 2.28 angstroms, which is in the right ballpark, the bigger the R groups are, the bigger the cone is. The bigger the R groups are, the bigger this angle right here is, this apex angle. This apex angle is known as the cone angle. And so the bigger the R groups get, the bigger the cone gets. And so if I now make my R groups bigger, notice now I have to draw a bigger cone. So the bigger the R groups, the bigger the cone. And so why do we really care about the size of a phosphine ligand. And so size is good, but what you have to think about is the bigger the phosphine is, the less of those phosphines you can put around a transition metal center. And when this idea of cone angle really was start to be introduced, it was introduced by Chadwick Tolman. He was working at DuPont. And a chemical process they were really interested in was hydrocyanation of butadiene. And the reason you're interested in hydrocyanation of butadiene is this makes a diponitrile. A diponitrile is then used to produce nylon on an industrial scale. And what they found was that if they used a series of phosphines shown here, they all are electronically pretty similar. Look at the cyanide stretching frequency and the CO stretching frequency. Nothing is really all that different. But notice that the rate of this oxidative addition reaction, and so this is the oxidative addition, OA, of HCN to this nickel center here. Well, this nickel center here is a 3-coordinate nickel center. Everything you start with that you weigh out was a 4-coordinate nickel center. Well, the bigger the phosphine is, the more likely you're going to get phosphine dissociation, because the phosphine groups start to pressure one another and bully one of the phosphines out. And so notice the huge increase in rate is shown with this orthotoluol derivative. Well, when you have an orthotoluol derivative, the methyl group is ortho. That puts a lot of steric pressure on the transition metal center. And notice how much faster the rate speeds up. Well, this orthotoluol substituent here also has, or this phosphine, has the largest cone angle. And so the larger the cone angle is, the more you're going to promote low-coordinate compounds. DuPont used this quite strategically to generate low-coordinate nickel species in solution. They then did rapid oxidative addition of HCN, and they got you straight into the catalytic cycle for the hydrocyanation of butadiene. And so this is really, really important. The larger the cone angle, the less of those phosphines you're going to be able to put on a transition metal center. And so notice here they've actually now determined the cone angle of a huge number of phosphine ligands. You can do this kind of with models, but people are largely doing this computationally now. And a second parameter they've introduced is known as buried volume. Buried volume was actually really pioneered with NHC ligands, which are shown over here, but they are kind of, the concept is exactly the same. The bigger the cone angle, the bigger the buried volume, the bigger the ligand is. And so what you'll notice here is one really important one, tritert-butylphosphine. Notice its cone angle, and the red on red doesn't look right, but look at its cone angle. It's 182 degrees. Well, if you think about it, if you think about a transition metal complex as being a sphere, what this really means is that you're only at most going to really be able to put 2 tritert-butylphosphines around a single metal center. And so if you want low coordinate compounds, you want phosphines with large cone angles. And so recently, the triadamantal was finally synthesized and showed some really interesting properties. Notice its cone angle is up to the same, basically the same as tritert-butylphosphine. You can only put 2 of those around a transition metal center. And so how are we going to actually use this? Because now we know we can determine cone angles. We can also determine the electronic properties by using at the CO stretching frequency. And so if we're dealing with a catalytic process, are we going to be able to kind of rationally decide what phosphine to use? And we can. We can actually use now what's known as Tolman's steric and electronic map. And so on the y-axis is plotted the CO stretching frequency, and on the x-axis is plotted the individual cone angle. And so how are you going to use this map? Well, I'd focus on the corners of the map. You have trifluorophosphine, trimethylphosphine, tris pentafluorophenylphosphine, and tritert-butylphosphine. That's not a plus sign, that's a tert-butyl ligand. And so when you look at these, you can actually intuitively already figure out what kind of phosphine they are. Trifluorophosphine is going to be a poor donor. It has a very electron withdrawing fluorine atoms. Trimethylphosphine is an all alkyl phosphine. You know it's going to be a pretty good donor as well, or you know it's going to be a pretty good donor. Tris pentafluorophenylphosphine features a electron withdrawing phenyl groups. It's probably not going to be too good of a donor. And tritert-butylphosphine, you already know, is an excellent donor. Notice that the excellent donors have low CO stretching frequencies. The poor donors have higher CO stretching frequencies. And now here is the x-axis for your cone angle. The bigger the phosphine, the bigger the cone angle. And so we can really break this map up into quadrants, those that have small size and are poor donors, like trifluorophosphine, those that have small size and are good donors, like trimethylphosphine, those that have large size and are poor donors, like tris-pentafluorophenyl phosphine, and those that are large and good donors, like tritert-butylphosphine and tricyclohexylphosphine. And so if we kind of break this into the quadrants, what you'll notice is that this quadrant up here, the ones that are big and poor donors, it's kind of a sparse quadrant, but can be extremely useful. And in fact, this phosphine right here, it's actually a phosphite ligand. There's a PO linkage to the phenyl unit. This phosphite proved to be really, really important back in the early 80s. And it proved to be really important in the hydroformylation of 2-methyl-1-hexene. And so this is an extremely challenging substrate, at least back in early 1980s, due to the fact that this alkene was disubstituted. And so when they performed hydroformylation on this, and notice hydroformylation is just the addition of an aldehyde functionality using H2 and CO. The other H from the H2 ends up at this position. And so this was a challenging substrate, but it turned out that using large cone angle phosphite ligands proved to be the special sauce. And so in hydroformylation, the mechanistic catalytic cycle has been known for quite a long time. It looks super complicated, but don't focus on the branched half over here. Just focus on the linear half. You got linear products in this case. But what I want you to pay attention to is the actual catalytic loop. And so you start with what you weigh out, which is a pre-catalyst, a rhodium-1 D8 18 electron compound. In order to enter the catalytic cycle, you must lose a CO ligand. When you lose a CO ligand, you now generate a lower coordinate rhodium-1 D8 16 electron square planar complex. That complex is able to pick up an olefin, so it binds an olefin, generating compound 3. You then get an insertion step into the rhodium hydride, generating this rhodium alkyl. CO rebinds to the rhodium. You get a new 5-coordinate rhodium complex. It then undergoes an insertion with CO to give you compound 6. Oxidative addition of H2, followed by rapid reductive elimination, then generates your product. And so what you need, or the catalytically active species, is low coordinate. Well, if it's low coordinate, that means it's probably going to be supported by large cone angle ligands. Furthermore, you have to lose CO to enter the catalytic cycle. And so what is going to promote the loss of CO? Well, it turns out that these large cone angle phosphine ligands do. And so if you look here at a table showing the turnover rate right here, you'll notice that the large cone angles lead to a large degree of turnover. And so why is that? Well, the large bulky phosphate ligands induce low coordination numbers, but the phosphite ligands are key because they promote the loss of CO. And so here is what the actual phosphite ligand looks like. So you can imagine it is pretty big. But how is it inducing the loss of CO? Well, notice that you don't have PC bonds, you have PO bonds. Well, O is obviously more electron negative and more electron withdrawing than carbon. And so what happens is that this back bonding interaction that I introduced to you before is less prominent. And so now you don't have R groups, you actually have OR groups. Well, if you have OR groups, the phosphine is less electron donating. And so the phosphine, in this case a phosphite, is actually pulling electron density towards it. Well, if it's pulling electron density towards it, the metal then has less electron density. If the metal has less electron density, there's going to be less back bonding. If there's less back bonding, the MC bond remains as a MC single bond. It doesn't adopt any MC double bond character. Well, an MC single bond is going to be a lot easier to break than something that starts to look like an MC double bond. Therefore, the electron withdrawing ability of the large phosphite ligand starts to siphon electron density away from the transition metal center. That minimizes back bonding. If the back bonding is minimized, the CO functionality becomes more labile. It then falls off, and you can enter the catalytic cycle. Really, really cool stuff. If you really are interested, 1983, they figured this out. And so that was monodentate ligands. Monodentate ligands are ones that only bind through a single p atom. It's much more common to encounter bidentate ligands, even tridentate and tetradentate ligands. And so here are some of the most common bidentate ligands. Bidentate ligands bind through 2 donor atoms. Tridentate ligands bind through 3. Tetradentate ligands bind through 4. But the most common are bidentate ligands, and many of these are commercially available. They're usually quite easy to make, and the chiral ones like BiNAP and DuPhos can be used to facilitate asymmetric induction. BiNAP features no chiral centers, but it is axial chiral. It cannot rotate about that CC double bond. It then leads to a ligand that has no mirror plane, no inversion center, and is therefore chiral. And so what these ligands can do is they can engage in what is known as chelation. And so all of these ligands feature more than one donor atom that can bind to a transition metal center, and it forms then a chelate. This right here is known as your chelate. And notice that you form a ring. And in fact, this ability to form a ring and form a chelate is extremely important in transition metal chemistry, so much so that there's actually an effect named for it, the chelate effect. And so what has been found is that when you form a chelate, it is much more thermodynamically favorable than using more than one monodentate ligand. And take, for example, this example here. It's simple substitution on a copper center, replacing the water molecules with ammonia versus ethylene diamine. Ethylene diamine is shown here in the previous slide. Ethylene diamine, often abbreviated as EN. And so notice that the reaction with ethylene diamine is extremely thermodynamically favorable, much more so than substituting the water by 2 ammonia ligands. And so why is that? Well, delta G equals delta H minus T delta S. Delta G also equals negative RT ln KEQ. All right. And so notice that the driving factor, and especially the one they talk about in your textbooks, appears to be the entropy. The more positive the entropy, the more thermodynamically favorable the reaction will be. And so why is the entropy so favorable in the case of ethylene diamine? Well, remember, entropy is disorder. The more molecules that are present in solution, the more disorder you have. And so if you look at the reactants of both sets of reactions, you have 3 molecules over here. You have the copper molecules. Sorry about that. You have 3 molecules on the left-hand side of the arrow. Over here, you only have 2 molecules. You just have the copper complex and ethylene diamine. Well, when the top reaction occurs, you end up with 3 molecules on the right-hand side of the arrow. On the second reaction, notice you end up with 3 molecules on the right-hand side of the arrow. You go from 2 molecules to 3 molecules. The ethylene diamine displaces 2 water molecules. When it displaces 2 water molecules, you get a much bigger hit on your entropy. The entropy goes way up. You're starting with 2 molecules. You're getting more disordered and moving to 3 molecules. And therefore, the delta G is significant. Well, if you look at the actual values here, notice that the enthalpy is also much more favorable in the case of chelates. Now, why is that? The delta H is also more negative for chelates. Why would it be more thermodynamically favorable to start forming rings? Well, remember, if you're comparing ammonia to ethylene diamine is more basic than ammonia. This is a pseudo-methyl group. Remember, methyl groups add S character to bonds. That leads to a more basic nitrogen lone pair, more P character in that lone pair. Well, if it's a better base, it's going to bind more effectively to the cationic copper center. That's thermodynamically favorable. Furthermore, notice this. Both the lone pairs in the conformation I drew are pointing at one another. There would be electron-electron repulsion. The second you introduce a metal center, notice what happens. That electron-electron lone pair repulsion goes away because the lone pairs are now bound to the transition metal center. This is what's driving the enthalpy. This is why with chelates you also have an enthalpic component in which now the delta H is more negative, the delta S is more positive. This all leads to a more negative delta G, and the more negative delta G leads to a bigger KEQ. The reaction is driven much farther to the right. Very interesting stuff. And so the bottom line here is that multidentate ligands, bidentate, tridentate, tetradentate ligands give you more thermodynamically stable transition metal complexes than their monodentate counterparts. And so when we form these chelates, we're forming a ring. And so 5 and 6 membered rings at a transition metal center are typically best. You may ask yourself, well, why is that? Well, the reasons are actually very similar to organic chemistry. Remember, cyclopropyl and cyclobutane rings, 3 and 4 membered rings, have a huge degree of strain. Well, that huge strain, you really don't want that in a transition metal complex. 7, 8, and even bigger rings, the strain isn't so much, starts to increase in some strain, but you get weird conformations, and transition metal centers usually don't fit very well into weird conformations. So 5 and 6 membered rings, which in organic chemistry are highly unstrained, 6-membered rings effectively have no strain, also here are favorable. You want your metal to engage and be in a 5-membered ring, like these, or a 6-membered ring, like the tridentate triphos derivative. And so 5 versus 6, which is better? And so I point you to this quote, which, like in my last lecture, these older papers have quotes that read like I feel like I'm reading Old English. Increase of chelate ring size from 5 to 6 membered in a complex will increase the stability of complexes of smaller radius relative to larger metal ions. Man, you read that and I think, man, I don't even know what that really means. Well, what they're trying to say is that if you're going to form a 6-membered ring, use a bidentate ligand and have a 6-membered ring, the metal would prefer to be small. And so if you're forming 6-membered rings at a transition metal center, you want your metal to be small. If you want your metal to be small, you're looking at a first-row transition metal complex. And why would you want the metal to be small? Well, remember your chair conformation in a cyclohexyl ring. It's almost entirely unstrained. The CCC angles are 109.5 degrees. You have no strain. Well, if the metal can kind of mimic a carbon center, be approximately the same size as a tetrahedral carbon, you'll maintain that low strain in the chair conformation. However, the size of the metal increases. If the metal gets bigger and bigger and bigger, your chair starts to flatten out. If your chair starts to flatten out, you get an increase in the amount of strain, unfavorable interactions in the backbone of the 6-membered ring. This is highly unfavorable. And so what you often observe is this observation here, that first-row transition metal complexes are typically ligated by chelates that form 6-membered rings. As you drop down to the second and third row of the transition metal series, the metal atom gets bigger, and you tend to see chelates that form 5-membered rings at those transition metal centers. And so why 5-membered rings at bigger metal centers? Well, I just told you that a chair conformation, a 6-membered ring, if you can maintain a chair conformation, you're looking pretty good. And the best way to do that is have what would be the carbon atom here, the sp3 hybridized carbon atom. If the metal center is of similar size, and so we're talking first-row transition metal, you remain pretty unstrained. Well, if a 5-membered ring becomes unstrained or has minimal strain, what you'll notice is that the angle decreases considerably, down to 69 degrees. Also, the bond lengths increase as well. Well, if you want longer bonds, what we're going to be talking about is swapping now nitrogens for phosphorus. You'll have longer bonds then. You also want a metal center that's going to support more narrow angles. Well, if you want longer bonds between the metal and now the ligand donors, and you want smaller angles, we're really talking about moving right into hard, soft, acid, base theory. And so you want metals that are larger. That means softer metals. You want metals that are going to form now longer bonds. Well, they form longer bonds to phosphorus centers than to nitrogen centers. And so we're going to now be matching a soft metal with a soft phosphine. And what's really important here is as you're forming 5-membered rings, think about the geometries of transition metal complexes. And I'm going to do my next lecture on the actual geometries to talk more about them. But you have an octahedral transition metal complex here. Notice that the LML angles shown here are 90 degrees. You can have square planar transition metal complexes. Notice that the LML angles here want to be 90 degrees. You can have trigonal bipyramidal transition metal complexes. Well, the ligands that are in the equatorial position and the ligands in the axial position, the LML bonds, will be 90 degrees. But if you have tetrahedral compounds, the LML angles are looking like 109.5. Tons of transition metal complexes that are tetrahedral are D10. And so they're inherently labile. I'll get more into that later. But if you're going to form a 5-membered ring, notice that the small angle is not going to match now the big angle in the metal center. You typically get very labile complexes. They often are very unstable. And so tetrahedral compounds, it's sometimes very difficult to get your chelate to match with the geometry of the transit or what the metal wants. And so, well, if the metal is starting to prefer angles close to 90 degrees, can you get the chelate to match that? And so what we're talking about now is trying to match the geometry of the transition metal center with the bond angles, with the bond lengths. But there's a second piece, the ligand. Well, if the ligand is forming a chelate, there's two different donors. There's two donor atoms that now are going to bind to the transition metal center, like so. And so what's really important is the spacing between the two donor atoms, in this case, phosphorus. And so here we got the pp distance fixed at 3 angstroms. And what you'll notice is that if the MP bonds are longer, the longer the MP bonds, the more the PMP angle can contract. If the MP bonds shorten, the PMP angle must open up. If they get shorter, the angle can actually open up even farther. And all this is based just on simple geometry. Here we're just forming a triangle. You can then invoke Pythagorean theorem here, and you can roughly calculate what your expected PMP angle would be. This PMP angle, or this ligand-metal ligand angle, is known as the bite angle. And so notice that if you have a fixed distance between the two donor atoms, now as the MP bond length gets longer and longer and longer, well, if that angle is longer, if the bond length is longer and longer and longer, the PMP angle can get smaller. But the second piece is now going to be controlling that spacing between the two donor atoms, in this case, the PP spacing. And so how are we going to actually control that PP spacing? Well, we can control it with a carbon spacer, or the linker between the two donor atoms. And so now if you compare DPPM, diphenylphosphenomethane, to DPPE, diphenylphosphenoethane, to DPPPP, diphenylphosphenopropane, and DPPPF, diphenylphosphenoferrocene, here's ferrocene. Notice, as you increase the distance between the two donor atoms, so that both donor atoms are phosphorus. Well, if you have a 1-carbon donor, the PP spacing is not very big. 2-carbon spacer, the distance gets larger. 3-carbon spacer, the distance gets larger. A ferrocene spacer, the distance between the two P centers is now the largest. And what we know experimentally is that the MP bond length, is approximately 2.305 angstroms. Well, if it's approximately 2.305 angstroms, the more we increase the distance between the two P centers, the larger the bite angle can be. And experimentally, we observe this. Notice the blue arrow tells you that the bite angle, so the PMP angle using diphenylphosphenomethane, is usually approximately 74 degrees. As you open up the spacer or add more carbon atoms in the spacer, DPPP, it's usually about 86 degrees, the bite angle. DPPPP, it goes all the way up to 90 degrees. And in DPPF, you're hovering around 100 degrees. The PMP angle, the bite angle, gets larger as the spacer, or the distance between the two donor atoms, gets larger. And so how are we going to actually now use this? We need to figure out how we're going to be able to use the bite angle, or what you expect the bite angle to be to form transition metal complexes. And a quote I got from this paper right here, I think really nicely gives you the information. The narrow distribution of bite angles observed are an indication that the PMP angle in monomeric complexes containing ppm fragments with small PMP angles is predominantly determined by the pp distance defined by the ligand backbone. If a ppm complex is formed, the measured bite angle reflects the ligand preferences rather than the metal requirements. All right, and so experimentally, again, notice the MP bond lengths. They actually all are pretty close to the 2.315 angstroms that they use in the calculations. Well, now notice that the bigger the spacer between the two donor atoms, here's a 1-carbon bridge, diphenylphosphanomethane. These all have 2 carbon bridges, 3 carbon bridges, 4 carbon bridge, ferrocene bridge. Notice that as the bridge starts to get bigger and bigger and bigger, both the calculations and the experimental bite angle gets larger and larger and larger. And so notice, though, the 2-carbon and 3-carbon bridges in particular, those bite angles, those PMP angles, are really hovering towards 90 degrees. And I think that this really is indicative that there's 2 different phenomena going on. The metal wants to be around 90 degrees. Well, these ligands also want to be around 90 degrees, depending on the spacer. If the spacer is a 2-carbon spacer between the 2 phosphines, you're going to form a 5-membered ring. If it's a 3-carbon spacer between the 2 phosphines, you're going to form a 6-membered ring. This is all trending towards 90 degrees. If your chelate is trending towards 90 degrees, the metal wants to be around 90 degrees, you're going to get very stable transition metal complexes. And so people have done this. But what's really interesting about bite angles is you can use them to dictate reactivity. And so what do I mean? Well, take, for example, this M should be a palladium. But take, for example, these 2 palladium complexes shown here. One is ligated by diphenylphosphanomethane, 1-carbon bridge. The other is ligated by diphenylphosphanobutane, a 4-carbon linker between the 2 phosphoruses. Well, notice the bite angles. And so the MP bite angle in the DPPM is approximately 73 degrees. In the other complex, it opens up all the way to 94 degrees. Well, what does that actually mean for the complex itself? Both of these complexes are square planar. And so the bigger the angle is, so notice the palladium P angle here is bigger, what that does is it smushes the C and X groups closer together. Well, if you smush the C and X groups closer together, you could trigger bond formation. And in fact, this is how bite angles can be used to trigger bond formation. And so in this cover art off the paper back in 2009 shows Pac-Man here, this Pac-Man right here with a large bite angle. It's got a wide bite angle, and that's forcing C and X close together. It's inducing some strain in the bite angle, but it's really forcing C and X close together. Well, if C and X are forced close together, C and X can actually form a bond. This bond, if you go from palladium 2 to palladium 0, is known as reductive elimination. And so you're likely, the bigger the bite angle, especially with palladium 2 complexes, the more you smush the C and X groups closer together. As they get smushed closer together, you're then going to start to trigger bond formation. And this was used to actually facilitate a transformation that was thought to be impossible. And so aryl CF3 bonds, like the phenyl CF3 bond shown here on the right, are extremely important in the pharmaceutical industry. Fluorination is found in many of the new drugs that come out, and palladium is used to often form some of these very crucial CC bonds. Well, the reductive elimination of the phenyl CF3 was never observed until 2006. And what Vlad Grushin's lab did was he used the wide bite angle Xanthos ligand. This is Xanthos in the backbone here. Xanthos has a bite angle of approximately 110 degrees. And so the P palladium P angle now opens up to approximately 110 degrees. This is a square planar transition metal complex. That angle wants to be 90 degrees. Well, it's occupying more space. That forces CF3 and phenyl into closer proximity. Turns out you just heat this just a little bit for a few hours, and you then reductive eliminate the phenyl CF3 group. Other bidentate ligands were used that had smaller bite angles. Diphenylphosphanobenzene, diphenylphosphanoethane, diphenylphosphanopropane, and TMEDA. All of these bidentate ligands, in addition to 2 monodentate triphenylphosphines, were all tested for this reaction. None of them worked. The bite angle is key. The bigger the bite angle, the more you smush CF3 and phenyl close together, the more they're squeezed into close proximity, they're more likely to trigger bond formation. And this critically important transformation is now used extensively in the pharmaceutical industry. Here's 3 molecules that have aryl CF3 bonds. You may not recognize them at all by their names, but what they all are billion-dollar drugs. Every single one of these is a billion-dollar drug. This ability for chemists to form aryl CF3 bonds, especially using palladium, which is so common in the pharmaceutical industry, is critical. And so by using a wide bite angle diphosphine, you now can trigger aryl CF3 reductive elimination. You can get streamlined access to these synthetic targets. In principle, this could lower the price of the drugs. You make them easier, you could lower the price. It's up to the companies to do that, though. But critically important bond formations. And so to summarize now, I finished part 2. Monodentate ligands, especially monodentate phosphines, you can measure how big they are using the cone angle here. The larger the cone angle, the larger the phosphine. If you now use this in conjunction with the electronic component, which you can do with the CO stretching frequency, you can get the what is known as the Tolman steric electronic map, which is shown kind of small there. But what's really, really important is that some of the biggest phosphines, like tritert-butylphosphine, are some of the best donors. And furthermore, the bigger the phosphine is, the fewer those phosphines you can fit around transition metal center. You can then get low coordinate compounds. If you get low coordinate compounds, many of these are super important in catalytic processes like the hydroformylation reaction I showed a few minutes ago. If you then kind of, let's say, upgrade and use bidentate or multidentate ligands, the PMP angle is known as the bite angle. The bigger the bite angle, the less room there is for other ligands, and both the most popular chelates and the transition metal center both like to hover around 90-degree bite angles. This is a recipe for making very stable transition metal complexes, and I hope you'll make some very stable transition metal complexes. And furthermore, I hope you learned something. This concludes part 2 of this lecture. Next lecture is coming soon. It's going to be on geometries.